So here's something you've probably never really thought about, even though you've seen it thousands of times. The moon. It's up there right now, or it was a few hours ago, or it will be soon, hanging in the sky like it's the most natural thing in the world. And it is, in a way. It's been there your entire life. It was there for every human being who ever lived, every civilization that ever rose and fell, every pair of eyes that ever looked upward and wondered. But here's what's wild about the moon, the thing that most people never stop to consider. It shouldn't really be there. Not like that. Not that big, not that close, not in that particular orbit. The moon is, by the standards of planetary science, genuinely weird. It's enormous relative to the Earth, far larger than any other moon compared to its parent planet in the entire inner solar system. Its diameter is about a quarter of Earth's. Jupiter's moons are big in absolute terms, sure, but compared to Jupiter itself, they're specks. Our moon is a companion, not a speck, and it's slowly drifting away from us, a few centimeters every year, and has been for billions of years. It has no atmosphere to speak of, no magnetic field, no active geology. And yet, without it, life on Earth might never have evolved at all. The tides, the stable axial tilt, the length of our day, all of it is tangled up with this gray, cratered, quietly extraordinary companion that most of us barely glance at. And that's what we're going to talk about tonight. Everything about the moon, how it got there, what it's made of, why it looks the way it does, why it behaves the way it does, and why it matters so much more than you probably think. We're going to take it slow, start at the very beginning, the very, very beginning, and just walk through the whole story together. No rush. If you drift off somewhere along the way, that's perfectly fine. The moon will still be there when you wake up. It always is. Let's start with the most basic thing. The thing you can see with your own eyes on a clear night. No telescope, no equipment, just looking up. The moon is bright. Surprisingly bright, actually. On a full moon night, you can walk around outside, read large print, see shadows on the ground, and yet the moon itself doesn't produce any light at all. Zero. It's a rock. A big, dry, airless rock, and every bit of light you see when you look at it is reflected sunlight. That's it. The sun shines on the moon bounces some of that light toward Earth, and that's what you see. And here's the thing. The moon is not even particularly good at reflecting light. It only bounces back about 12% of the sunlight that hits it. 12%. That's about the same reflectivity as worn asphalt, an old parking lot. If you could somehow put fresh snow on the moon, which reflects about 80 to 90% of light, a full moon would be so bright it would cast sharp, vivid shadows, and you could comfortably read a newspaper by it. The moon looks bright to us, only because there's so much sunlight hitting it, and because the night sky is so dark by comparison. Our eyes adjust, and in that darkness, even 12% of the sun's light reflecting off a body, 2,160 miles across, is more than enough to light your way home. Now, the ancient Greeks figured out that moonlight was reflected sunlight surprisingly early. A philosopher named Anaxagoras, born around 500 BCE in Clazomene, in what's now Western Turkey, declared that the moon was a rocky body that shone by reflected light from the sun. This was a radical thing to say. Most people at the time thought of the moon as a divine object, a god or a manifestation of one, something fundamentally different from earthly matter. Different cultures had different stories. The Mesopotamians associated the moon with the god Sin, whose crescent adorned temples across the ancient Near East. The ancient Egyptians worshipped Thoth and Khonsu as lunar deities. In Chinese mythology, Chang'e lives on the moon, having drunk an elixir of immortality. The Hindu tradition associates the moon with Chandra, a god who rides a chariot pulled by 10 white horses across the night sky. Every culture looked up at the same moon and saw something different, but almost all of them saw something sacred, something luminous and alive. Anaxagoras said no, it's a rock, like the rocks on the ground, just very far away and very big. He even reportedly said the moon was about the size of the Peloponnese, the large peninsula in southern Greece. That estimate was wildly off. The moon is actually about the size of Africa, with a diameter of about 2,160 miles. But the insight that it was a physical object of finite size, reflecting the sun's light, that was revolutionary. And Anaxagoras paid a price for it. He was charged with impiety, with insulting the gods, and had to flee Athens to save his life. Some accounts say he was sentenced to death in absentia. Being right, in ancient Greece, could get you killed. But the idea survived, because good ideas tend to, even when the people who propose them don't. Other Greek thinkers built on Anaxagoras's foundation. Democritus suggested the dark markings on the moon were the shadows of mountains. Aristotle, oddly, regressed. He accepted that the moon shone by reflected light, but insisted it was a perfect sphere, made of celestial material, fundamentally different from earthly rock. That distinction would dominate European thought for nearly 2,000 years, until Galileo shattered it with a telescope. But in the Greek tradition, the understanding that the moon was a physical body, lit by the sun, was established, and it was the essential foundation for everything that followed. And here's the thing about Anaxagoras's insight. Once you accept that the moon shines by reflected sunlight, a cascade of other understanding follows almost automatically. Because if the moon is a sphere lit by the sun, then the way it looks from Earth, its phases, makes perfect geometric sense. And the phases of the moon are one of those things that seem mysterious until someone explains them, and then they seem so obvious, you can't believe you ever found them confusing. Think about it this way. The moon is a ball. The sun is shining on it from one direction. At any given moment, exactly half the moon is lit up, the half facing the sun, and the other half is in shadow. That never changes. There's always a bright half and a dark half. What changes is how much of that bright half you can see from where you're standing on Earth. When the moon is between the Earth and the sun, roughly speaking, on the same side of us as the sun, you're looking at the dark half. The lit half is facing away from you, toward the sun. That's a new moon. You can't see it at all, or maybe just the faintest sliver if the geometry is right. Then, as the moon moves along its orbit, you start to see more and more of the lit half. A thin crescent appears on the right side, if you're in the northern hemisphere at least, growing night by night. After about a week, you can see exactly half the lit side. That's the first quarter, though people often call it a half moon, which makes sense because it looks like half a circle. The name first quarter refers to the moon being 1/4 of the way through its orbital cycle, not to the amount you can see. Keep going, and the lit portion grows past half into what's called a gibbous moon. A lovely word, gibbous, from the Latin gibbus meaning hump or hunchback. And then, about 2 weeks after new moon, the Earth is between the moon and the sun, and you're looking directly at the fully lit half, full moon, everything bright, everything visible. Then the whole process reverses. The lit portion shrinks from the left side, passing through waning gibbous, third quarter, waning crescent, and back to new moon again. The whole cycle takes about 29.5 days. That's a synodic month, the time from one new moon to the next, and it's the origin of our concept of a month in the first place. The word month literally comes from moon. So does Monday, Moon's Day. The moon is baked into our language, into our calendar, into the way we organize time itself. And here's another thing about phases worth spending a minute on, because it clears up a misconception that's surprisingly common. The phases of the moon have absolutely nothing to do with Earth's shadow. Nothing. A lot of people think the crescent moon is caused by the Earth casting a shadow on the moon, and it seems like such a reasonable explanation that it persists even among people who are otherwise pretty science literate. But think about it. If the crescent were caused by Earth's shadow, the shadow would always be circular, because the Earth is round, and a crescent is not a circular shadow. The crescent shape is simply the geometry of seeing the edge of a sphere's lit hemisphere from an angle. When you look at a ball under a desk lamp and tilt it so you can only see a sliver of the lit side, you see a crescent. No shadow needed. Earth's shadow on the moon is what produces a lunar eclipse, which is a completely different phenomenon, and it happens rarely, not every month. The monthly phases are pure geometry, the angle between the sun, the moon, and your eyes. There's also a lovely detail about the crescent moon that you can check for yourself on the next clear evening. When the moon is a thin crescent, you can often see the rest of the moon's disk faintly glowing, a dim, ghostly illumination of the dark portion. This is called earthshine, and it was first correctly explained by Leonardo da Vinci around 1510. What you're seeing is sunlight reflecting off the Earth, hitting the dark side of the moon, and bouncing back to your eyes. The Earth, seen from the moon, would look like a brilliant blue-white disk, much larger and brighter than the full moon appears from Earth, because the Earth is bigger and more reflective. That earthshine illuminates the lunar night side just enough for you to perceive it. You're looking at light that has bounced off two worlds, from the sun to the Earth to the moon to your eyes. Leonardo figured that out over 500 years ago, before telescopes even existed, just by looking carefully and thinking clearly. That's the kind of observation that makes you appreciate how extraordinary human perception can be when it's coupled with genuine curiosity. Now, here's a detail that trips a lot of people up. The moon doesn't go around the Earth in exactly the same plane as the Earth goes around the sun. The moon's orbit is tilted about 5 degrees relative to Earth's orbital plane, which astronomers call the ecliptic. 5 degrees doesn't sound like much, but it matters enormously, and here's why. If the moon's orbit were in exactly the same plane, then every single new moon would produce a solar eclipse. The moon would pass directly between the Earth and the sun and block the sunlight. And every single full moon would produce a lunar eclipse, with the Earth's shadow falling on the moon. Eclipses would happen twice a month, every month, like clockwork. But they don't, because of that 5-degree tilt. Most of the time, at new moon, the moon passes a little above or a little below the sun from our perspective, missing it entirely. And at full moon, it passes a little above or below Earth's shadow. Eclipses only happen when the moon crosses the plane of Earth's orbit at just the right moment, when it's near one of the 2 points where its tilted orbit intersects that plane. Those points are called nodes, and eclipses can only occur near the nodes. That's why eclipses are relatively rare and don't happen every month. But we'll come back to eclipses later, because they deserve their own long, slow exploration. There's far more to say about them than most people realize. But the Greeks didn't stop at understanding phases. They used the moon to measure the cosmos. In the 3rd century BCE, Aristarchus of Samos, one of the most underrated geniuses in the history of science, devised a method to estimate the relative distances and sizes of the sun and moon using nothing but geometry and careful observation. During a first quarter moon, when exactly half the visible face is illuminated, the sun, moon, and earth form a right triangle, with the right angle at the moon. By measuring the angle between the sun and moon in the sky at that moment, Aristarchus could calculate the ratio of their distances. His measurement was off. He estimated the sun was about 19 times farther than the moon, when it's actually about 390 times farther, because the angle is very close to 90 degrees and exquisitely hard to measure with the naked eye. But the method was sound, and the attempt was audacious. He was trying to measure the geometry of the solar system with nothing but his eyes and a protractor, 2,300 years before anyone had a telescope. And he also estimated the moon's distance at roughly 60 Earth radii, which is remarkably close to the actual value of about 60.3. That's extraordinary accuracy for the tools available. There's also a curious phenomenon worth mentioning, because it relates to how we perceive the moon, and it catches everyone off guard the first time they learn about it. The moon looks much larger near the horizon than it does high in the sky. You've probably noticed this. A rising full moon can look absolutely enormous, like it's inflated, filling a huge area of the sky. And then a few hours later, when it's overhead, it looks noticeably smaller. But here's the thing. It isn't actually bigger near the horizon. Its angular size is the same, about half a degree, regardless of where it is in the sky. You can verify this yourself by holding up a pencil eraser at arm's length. The moon will fit behind it, whether it's near the horizon or high overhead. What you're experiencing is the moon illusion, one of the oldest known optical illusions. And despite centuries of study, scientists still don't fully agree on what causes it. The most common explanation involves the brain interpreting the moon near the horizon as more distant, because it's next to trees, buildings, and the apparent dome of the sky, and compensating by perceiving it as larger, the way it does for distant objects in everyday life. But whatever the mechanism, the illusion is powerful. The harvest moon rising in autumn, enormous and orange over the horizon, is one of the great visual spectacles of the natural world, and it's partly an illusion created by your own brain. Now, here's something that genuinely puzzled people for a very long time, and it's so familiar that you might not even think of it as strange. Look at the moon on any clear night. Study the pattern of dark and light patches. That pattern, the face of the man in the moon, or the rabbit, or the woman reading a book, or whatever your culture sees in it, never changes. You always see the same face. Always. The same craters, the same dark patches, the same arrangement of features. You never see the back of the moon. Not from Earth, not ever. No matter what time of month or year. No matter where you are on the planet. And this might seem like a coincidence, or maybe it seems so natural you've never questioned it. But it's neither. It's the result of a physical process that took hundreds of millions of years to complete, and it's happening all over the solar system, not just here. The reason you always see the same face of the moon is that the moon rotates on its axis at exactly the same rate that it orbits the Earth. One rotation takes about 27.3 days, and one orbit takes about 27.3 days. So as the moon goes around the Earth, it turns just enough to always keep the same face pointed toward us. If this is confusing, try it with your fist and your head. Hold your fist out and walk it in a circle around your head, keeping the same side of your fist facing your nose the whole time. You'll notice your fist has to rotate exactly once for every trip around your head. That's synchronous rotation. If your fist didn't rotate at all, you'd see all sides of it. The fact that the moon shows us only one face means it's rotating at precisely the matching rate, and that precision is not accidental. This is called tidal locking, and it's an inevitable consequence of gravitational interaction over long periods of time. Here's how it works. The Earth's gravity pulls on the Moon, but it pulls a little harder on the near side than on the far side, because gravity decreases with distance. This difference in gravitational pull, this tidal force, creates a very slight elongation of the Moon, stretching it into a subtle football shape along the Earth-Moon axis. The elongation is tiny, maybe about 20 meters, but it's there. Early in the Moon's history, it was spinning faster than it orbited. The gravitational tug of the Earth on that slight bulge acted like a brake. If the bulge got carried ahead of the Earth-Moon line by the faster rotation, Earth's gravity pulled it backward, creating a torque that gradually slowed the spin. Over hundreds of millions of years, that braking brought the Moon's rotation into perfect synchrony with its orbit. Once locked, the bulge stayed aligned, the torque vanished, and the system settled into the configuration we see today. Now, the fact that we only ever see one face naturally raises a question. What's on the other side? The far side of the Moon, often incorrectly called the dark side, though it gets exactly as much sunlight as the near side. Dark, in this context, just means unknown, was a complete mystery until 1959, when the Soviet probe Luna 3 swung around the Moon and photographed it. The images were grainy and crude, but they revealed something nobody expected. The far side looks nothing like the near side. Where the near side has those large, dark maria, the lava-flooded basins that create the man in the Moon, the far side has almost none. It's heavily cratered highland terrain almost everywhere, bright and rough, with only a few small patches of basalt. The asymmetry is dramatic. Why would one hemisphere have vast lava plains and the other almost none? The leading explanation involves the Moon's crustal thickness, which is uneven. The near-side crust is measurably thinner, perhaps 20 miles thinner on average, than the far-side crust. This may trace back to the Moon's earliest history, when the near side, facing the hot, still molten young Earth, stayed warmer longer, so the crust there grew more slowly and never got as thick. When giant impacts later carved enormous basins on both sides, the magma beneath the thinner near-side crust had an easier path to the surface, flooding those basins and creating the dark maria. On the far side, the thicker crust acted like a cap, keeping the magma trapped underground. Same bombardment, different outcomes, all because of a difference in crustal thickness that may ultimately trace back to tidal locking itself. The face you see every night is literally shaped by the fact that it's the side facing Earth. Tidal locking isn't unique to our Moon, by the way. Most large moons in the solar system are locked. The Galilean moons to Jupiter, Titan to Saturn, Charon to Pluto. Charon and Pluto are even mutually locked, each forever showing the same face to the other, endlessly gazing across 12,000 miles of space. Give it enough time, and tidal locking is almost inevitable. There's actually a slight wobble to the Moon's locked face. It's not perfectly rigid in its orientation. The Moon rocks back and forth very slightly, an effect called libration, caused by the eccentricity of the Moon's orbit. It's not a perfect circle, so the Moon speeds up and slows down, but its rotation rate stays constant, and by the tilt of the Moon's axis relative to its orbit. Libration means that over time, we can actually see about 59% of the Moon's surface from Earth, not just 50. Little slivers of the far side peek around the edges at different times. But the remaining 41% was completely unknown until the space age. But here's the flip side of tidal locking, and it's even more fascinating. The Earth feels the Moon's tidal forces too. The Moon's gravity raises tides in our oceans. We'll explore that in depth shortly. But those tides are also very gradually, changing the Earth itself. The tidal bulge doesn't sit directly beneath the moon. Because the Earth spins faster than the moon orbits, the bulge gets carried slightly ahead of the moon's position. The moon's gravity, pulling back on that offset bulge, acts as a brake on Earth's rotation. Our days are getting longer, about 2.3 milliseconds per century. And as the Earth loses rotational angular momentum, the moon gains orbital angular momentum, moving to a slightly higher orbit. The moon is drifting away, about 3.8 centimeters per year, roughly the rate your fingernails grow. We know this with extraordinary precision because the Apollo astronauts left retroreflectors on the lunar surface, corner cube prisms that bounce light directly back, and scientists regularly fire laser beams at those mirrors and time the round trip to fractions of a nanosecond. Laser beams traveling 478,000 miles round trip, timed to billionths of a second, hitting mirrors left over 50 years ago. The precision is almost absurd. Run that recession backward, and the implications are staggering. The moon was closer in the past, much closer. 4.5 billion years ago, it may have been only 15 to 20,000 miles away, compared to today's 239,000. More than 12 times closer. It would have looked enormous, 15 to 20 times its current apparent size. The tides would have been monstrous, hundreds of feet high. The day was shorter, maybe 6 hours, maybe less. 6-hour day, colossal moon. Tides reshaping the young continents every few hours. That was the early Earth, and slowly, over billions of years, the moon drifted away, the tides weakened, the days lengthened, and the system calmed into what we know today. And this slow, patient dance between the Earth and moon, the tides, the recession, the slowing of days, it was the moon that helped Isaac Newton discover the law of universal gravitation in the first place. In the 1680s, Newton realized that the same force pulling an apple toward the ground was also pulling the moon toward the Earth, keeping it in orbit. The crucial test was whether gravity, diminished by the square of the distance, could account for the moon's orbital motion. Newton knew the moon's distance, about 60 Earth radii, and he knew the moon's orbital period. He calculated the rate at which the moon falls toward the Earth, because orbiting is falling, just moving sideways fast enough that you keep missing, and compared it to the rate a rock falls at Earth's surface. The ratio matched the inverse square of the distance. The same gravity that pulls a rock pulled the moon. This was the first quantitative proof that gravity is universal, that it operates the same way across the void of space as it does on the ground beneath your feet. The moon was the laboratory, and Newton's insight unified the heavens and the earth in a way that Galileo had only begun. And all of that raises what might be the most fascinating question in planetary science. How did the moon get there in the first place? Because a moon this big, this close, orbiting in this particular way, that demands an explanation. And the explanation turned out to be one of the most violent events in the history of the solar system. It involves a collision so catastrophic it essentially rebuilt two worlds from scratch. And it starts with a planet most people have never heard of. A planet called Theia, named after the Greek Titan goddess who was the mother of Selene, goddess of the moon. Even the name is poetic. To understand where Theia came from, you need to understand what the solar system looked like about 4.5 billion years ago. And it was nothing like the orderly, well-spaced system we live in today. Back then, the solar system was chaos. Pure, violent, beautiful chaos. Picture this. It's about 4.5 billion years ago. 4.5 billion. That's a number worth pausing on, because the human brain has no real intuition for it. If you counted to 4.5 billion at one number per second, without sleeping, without pausing, it would take you about 143 years. The entire recorded history of human civilization, everything from the first cuneiform tablets to the smartphone in your pocket, fits into about 5,000 years. 4.5 billion years is roughly 900,000 times that. The Moon has been orbiting the Earth for an almost incomprehensible span of time. So, 4.5 billion years ago, the Sun has recently ignited, surrounded by a vast rotating disk of gas and dust called the protoplanetary disk. Within that disk, stuff is clumping together. Tiny grains stick into pebbles. Pebbles form rocks. Rocks accumulate into mountain-sized bodies called planetesimals, and the process keeps escalating. The bigger an object gets, the stronger its gravity, and the more material it sweeps up. This is called accretion, and it's how planets are built, not neatly or gently, but through an eons-long demolition derby of collisions, mergers, and catastrophic impacts. By the time a few tens of millions of years have passed, the inner solar system contains maybe 20 to 50 Mars-sized protoplanets, along with countless smaller bodies, orbiting in paths that overlap and cross, and inevitably lead to collisions. Think of it like a crowded highway, where nobody is staying in their lane, and there are no exits. Every collision either shatters both bodies, with debris reaccumulating later, or merges them into something bigger. Over time, the number of protoplanets shrinks, and their sizes grow, until you end up with just a handful of survivors: Mercury, Venus, Earth, and Mars. But this process is stochastic, governed by chance encounters and gravitational perturbations from the forming Jupiter and Saturn. Small changes in starting conditions produce wildly different outcomes. Run the simulation again, and you might get 3 rocky planets, or 5, or a super-Earth where Mars is, or no Earth at all. Our particular arrangement is the result of specific collisions, at specific times, at specific angles. And the single most consequential of all those collisions, at least from our perspective, was the one that created the Moon. Here's the current best understanding: the giant impact hypothesis, first proposed seriously in the mid-1970s by William Hartmann and Donald Davis, and independently by Alastair Cameron and William Ward. About 4.5 billion years ago, a Mars-sized protoplanet, Theia, slammed into the young Earth. Some models place Theia's origin at one of the stable Lagrange points in Earth's orbit, where gravitational forces balance. What matters is that the impact was not head-on. It was a glancing blow, an oblique collision, and that turns out to be critically important. The energy involved defies comprehension. Roughly 100 million times greater than the asteroid impact that killed the dinosaurs. 100 million times. The surface of the Earth would have been completely liquefied. Not just the impact site, but the entire planet. The whole world glowing like a small star. Any prior atmosphere, any prior ocean, any prior solid crust. Vaporized. Gone. Theia's dense iron core plunged into the Earth and merged with Earth's existing core. Meanwhile, enormous quantities of rocky mantle material from both bodies were blasted into orbit, forming a vast, superheated debris disk, vaporized and molten rock, thousands of degrees hot, circling the shattered, glowing Earth like a nightmarish ring system. Some material was flung fast enough to escape entirely, lost to space, but most stayed, caught in Earth's gravity, and from that disk, the Moon coalesced. Relatively quickly, perhaps within centuries, maybe faster, the debris cooled, clumped, accreted, and formed a single body, born from catastrophe. born from the shattered remnants of two worlds that no longer exist separately. Every time you look at the moon, you're looking at the scar of that collision, the reassembled remnants of Theia and pieces of the old Earth rebuilt into something new. How do scientists know this? The strongest evidence comes from the Apollo missions. Those 6 successful landings between 1969 and 1972 brought back a total of about 842 pounds of lunar rock and soil. When scientists analyzed those samples, they found something remarkable. The oxygen isotope ratios in lunar rocks are virtually identical to Earth's, and oxygen isotope ratios are like fingerprints for planetary bodies. Every object in the solar system that formed in a different region has a slightly different mix of oxygen-16, oxygen-17, and oxygen-18. Mars rocks have different ratios than Earth rocks. Different asteroid groups have different ratios. But the Moon and Earth? Almost indistinguishable. This means the Moon is made largely from the same material as Earth's mantle, exactly what the giant impact predicts. If the Moon had formed somewhere else entirely and been captured by Earth's gravity, one of the older hypotheses popular in the 19th century, it would almost certainly have different isotope ratios. Capture is also dynamically very difficult. For a body as large as the Moon to be captured into a stable orbit, it would need to lose exactly the right amount of energy at exactly the right moment. Too little and it flies past. Too much and it crashes. Without some mechanism to dissipate energy, like a thick atmosphere or a third body, capture is essentially impossible for something this massive. If the Moon had fissioned off a rapidly spinning early Earth, the fission hypothesis, proposed by George Howard Darwin, Charles Darwin's son, in the 1870s, that would explain the isotope match beautifully, since both bodies would be made of the same material. But fission requires the early Earth to have been spinning at an impossibly fast rate, about once every 2.5 hours, which would need a source of angular momentum that's hard to account for. And if the Earth and Moon simply formed side by side from the same region of the disk, the co-formation hypothesis, you'd expect them to have similar compositions in every respect. But the Moon is dramatically depleted in iron and volatile elements compared to Earth, which co-formation can't easily explain. The giant impact hypothesis handles the iron deficit elegantly. Earth has a large iron core, about 1/3 of its total mass. The Moon has a tiny iron core, maybe 2 to 4%. In a giant oblique impact, the denser metallic cores of both bodies, Theia's iron core and Earth's existing core, would have merged and sunk to the center of the combined molten mass. The material blasted into orbit to form the debris disk was preferentially the lighter, rocky mantle material, not the dense metal. The Moon ended up iron poor, not because iron is rare in the solar system. It isn't. It's one of the most abundant metals, but because the physics of the impact selectively retained the iron deep inside the Earth and sent the silicate rocks into space. There are complications, naturally. If the Moon formed mainly from Theia's material, you'd expect the isotope ratios to differ slightly, since Theia presumably formed in a different part of the disk. The remarkably close match has led to several proposals. Maybe Theia formed very near Earth and inherited similar isotopes, or maybe the impact was so energetic that both bodies were completely vaporized and mixed. That second idea led to the synestia model, proposed by Simon Locke and Sarah Stewart around 2018. The impact transforms both bodies into a single, vast, donut-shaped structure of vaporized rock, from which the new Earth and Moon both condense. The mixing would be so thorough that isotopic differences are erased. It's elegant, still being debated. The broad outline, giant impact, debris disk, Moon, is solid. The details are being refined. That's how science works. You get the big picture, and then spend decades nailing down the specifics. The big picture, in this case, is a cataclysm unlike anything the inner solar system has seen since. But let's move forward in time now, because the story of what happened after the moon formed is just as fascinating as how it got there. And to tell that story properly, we need to talk about what the moon actually looks like up close, not just as a glowing disk in the sky, but as a world with its own geological history, its own dramatic past, its own stories written across its surface, in craters and plains and mountain ranges. And the first person to really see those stories, to look at the moon through more than human eyes and understand that it was a real, physical landscape, was Galileo Galilei, and how a simple telescope changed everything about our nearest neighbor in space is one of those pivotal moments worth telling slowly. It's late 1609. Galileo is a professor of mathematics at the University of Padua, in the Republic of Venice, in northern Italy. He's 45 years old, perpetually short of money. He has a mistress and 3 children to support, plus a brother who keeps borrowing money and not paying it back. And he's just heard about a remarkable new invention from the Netherlands, a device that uses 2 lenses in a tube to make distant objects appear closer. A spyglass. The first ones were crude, magnifying maybe 3 times, being sold as novelties and potential military tools. Galileo didn't invent the telescope. That credit usually goes to Hans Lippershey, a German-Dutch spectacle maker who applied for a patent in October 1608, though others were working on similar devices at the same time. But Galileo did something nobody else had done. He improved it dramatically, grinding his own lenses with extraordinary care, pushing the magnification first to 8 or 9 times, then to 20 or more, and then, crucially, he pointed it at the sky. That was the leap. Lots of people had spyglasses. Galileo was the one who looked up. In the autumn and winter of 1609 into early 1610, Galileo made observations that would reshape humanity's understanding of the cosmos. He saw the moons of Jupiter, 4 of them, orbiting the giant planet, proof that not everything orbited the Earth. He saw that Venus went through phases like the moon, which only made sense if Venus orbited the sun. He saw the Milky Way resolved into countless individual stars. He saw Saturn's rings, though his telescope couldn't resolve them properly. He thought Saturn had ears or handles, which must have been wonderfully confusing. But among the most revolutionary observations were his observations of the moon itself. When Galileo pointed his telescope at the moon, he didn't see a perfect, smooth, ethereal sphere. Aristotelian philosophy had taught for nearly 2,000 years that the heavens were perfect, unchanging, incorruptible, made of a 5th element called the quintessence, fundamentally different from the corrupt, changeable world below. The moon was supposed to be a flawless sphere of celestial perfection. What Galileo actually saw was a world, a rough, battered, mountainous world. He saw craters, dark, circular features with raised rims and shadowed interiors. He watched as the Terminator, the boundary between the lit and dark portions, crept across the surface, and just ahead of it, on the dark side, he noticed tiny bright spots, like islands of light in the darkness. He realized these were mountaintops, catching the first rays of sunlight, while the terrain around them was still in shadow. From the geometry, the distance of the bright spots from the Terminator, he estimated some peaks at several miles high. The lunar Apennines reach about 3 miles. He was remarkably close. He drew detailed sketches, showing a moon that looked nothing like the perfect celestial body of philosophy. It looked like a place, a battered, ancient, scarred place. He published in March 1610, in a slim book of about 60 pages, called Sidereus Nuncius, the Starry Messenger. He dedicated it to Cosimo II de' Medici, the Grand Duke of Tuscany, partly out of genuine admiration, but also because Galileo badly needed a better-paying job, and flattering the Medici was a time-honored strategy in Renaissance Italy. It worked. Cosimo appointed him chief mathematician and philosopher, and Galileo moved from Padua to Florence later that year. The impact of the Starry Messenger on European intellectual life was seismic. The moon was not a celestial perfection. It was a rough, mountainous landscape, more like the Earth than anyone had imagined. Not everyone was pleased. Some Aristotelian philosophers refused to look through the telescope at all, arguing that any imperfections they might see were artifacts of the lenses, not features of the heavens. One Florentine astronomer named Ludovico delle Colombe, whose name, appropriately enough, means "of the doves," argued that the moon was indeed perfectly spherical, and that the apparent mountains and craters were simply due to the crystalline material of the moon having varying degrees of transparency. Galileo, who had a sharp wit and little patience for nonsense, was not kind to delle Colombe in his replies. But the evidence was overwhelming, and the sharp Aristotelian distinction between corrupt earth and perfect heavens, maintained for nearly 2,000 years, had been demolished by a man with a tube and 2 pieces of glass. The universe was one continuous physical system, governed by the same laws everywhere. That idea is so foundational to modern science that we take it completely for granted. In 1610, it terrified people who had built their entire intellectual and spiritual worldview on the old certainties. Galileo called the dark patches Maria, Latin for seas, because they looked smooth, like water seen from a great height. The name stuck, even though we now know they're vast plains of solidified basaltic lava, dark, iron-rich volcanic rock that flooded enormous impact basins billions of years ago. The moon had a violent volcanic past, and the Maria are the evidence. Here's what happened, and the timeline matters, so let's walk through it carefully. In the moon's first few 100 million years, its interior was intensely hot. Residual heat from the giant impact, plus radioactive decay of uranium, thorium, and potassium. That heat produced basaltic magma deep in the mantle. Meanwhile, the surface was being absolutely pummeled by impacts during a period called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago, when a rain of asteroids and comets battered everything in the inner solar system. The moon, with no atmosphere to burn up incoming objects and no water or wind to erode the evidence, recorded every single hit. It's a cosmic record keeper of extraordinary fidelity, preserving impacts that happened billions of years ago with a clarity that Earth, with its active geology and weather and tectonics, cannot match. The largest impacts carved immense basins, circular depressions hundreds of miles across. The Imbrium Basin, one of the biggest visible from Earth, is about 720 miles in diameter, roughly New York to Chicago. The impactor was probably at least 150 miles across. The South Pole Aitken Basin on the far side is even larger, about 1,600 miles across, one of the biggest impact structures in the entire solar system. Then, over the next billion years or so, magma from the moon's interior welled up through cracks in the basin floors, flooding them layer after layer with dark basaltic lava. The lava spread across the floors, filled craters, smoothed terrain, and when it cooled, formed the dark, flat Maria we see today. Mare Imbrium, Mare Serenitatis, Mare Tranquillitatis, Oceanus Procellarum, all ancient lava plains filling impact basins. They're dark because basalt is darker than the ancient highland rocks, which are made of a lighter mineral called anorthosite, calcium and aluminum rich, originally formed in the Moon's magma ocean as it cooled. The magma ocean. That's a concept worth sitting with for a moment. When the Moon first accreted from the debris disk, the energy was so enormous that the entire outer shell, maybe several hundred miles deep, was completely molten, a global ocean of liquid rock with no solid surface at all. Just a churning, glowing sea of magma. As that ocean cooled over tens of millions of years, different minerals crystallized at different temperatures and separated by density. Dense minerals, olivine, pyroxene, sank to form the deep mantle. But plagioclase feldspar, lighter than the surrounding melt, floated to the top like cream rising in milk, accumulating into a thick, light-colored crust. That's the bright highland terrain you see today, the Moon's original crust, formed by flotation in a global magma ocean 4.5 billion years ago. The dark maria are younger volcanic floods. The bright highlands are the primordial surface, and you can see that difference, that geological timeline, with your naked eyes from 250,000 miles away. You're reading billions of years of history just by looking up. The highlands are saturated with craters. Every square mile hit and re-hit until adding a new crater destroys an old one. The maria have far fewer craters because they're younger. The lava buried the old ones, resetting the clock. This principle, crater counting, is a primary tool for dating surfaces throughout the solar system. The volcanic era ended about 1 billion to 1.5 billion years ago as the interior cooled and solidified. But the Moon isn't entirely dead inside. The Apollo seismometers, which operated from 1969 to 1977, detected 4 distinct types of moonquakes. Shallow moonquakes, originating within the upper 200 kilometers, were rare but could be quite strong, up to about magnitude 5, and they lasted extraordinarily long, sometimes ringing for over 10 minutes, because the dry, fractured crust transmits seismic waves with very little damping. On Earth, a magnitude 5 earthquake is over in seconds. On the Moon, it reverberates like a bell. Deep moonquakes, originating about 700 kilometers down, occurred in clusters at predictable times, driven by tidal stresses from Earth's gravity squeezing and releasing the lunar interior as the Moon moves through its slightly elliptical orbit. There were also thermal moonquakes, caused by the surface expanding and contracting as it cycles between extreme heat, about 127 degrees Celsius in sunlight, and extreme cold, about -173 in shadow, and meteorite impacts. The seismic data also revealed the Moon's internal structure. A small iron core, perhaps 300 to 400 kilometers across, surrounded by a partially molten layer, then a thick, solid mantle and crust. But by any measure, the Moon is geologically quiet now, a world that finished its drama long ago. Yet even in its quiet state, the Moon had one more surprise. Water. Not liquid surface water, impossible without atmosphere, but water ice, hidden in permanently shadowed craters near the poles. Craters whose floors haven't seen sunlight in billions of years, where temperatures drop to -250 degrees Celsius, colder than Pluto's surface. Cold enough that water ice, deposited by comet impacts or formed from solar wind interacting with the regolith, stays put, essentially forever. The evidence accumulated gradually, neutron detectors on orbiting spacecraft showing excess hydrogen near the poles, and then NASA tested it directly in 2009. The L-Cross mission crashed a spent rocket into the permanently shadowed Cabeus crater near the South Pole, and a following spacecraft flew through the debris plume. It detected significant water ice, plus mercury, carbon dioxide, and organic compounds. Estimates suggest hundreds of millions of tons of water at the poles, maybe more. And that changes everything about future exploration. Water can be split into hydrogen and oxygen through electrolysis, a process that's been understood since the early 1800s and requires only electricity, which can be generated from solar panels. The hydrogen is rocket fuel. The oxygen is both breathable air and an oxidizer for rocket propulsion. A lunar water supply means you could, in principle, refuel spacecraft on the moon instead of carrying all your propellant from Earth. And hauling propellant from Earth is enormously expensive. It costs roughly $10,000 per pound to reach low Earth orbit, and much more than that to reach the lunar surface. Every pound of water you can extract on the moon is a pound you don't have to launch from Earth. That's the concept behind what space engineers call in situ resource utilization, ISRU, and it's the reason the South Pole has become the most coveted real estate on the moon. Whoever establishes a reliable presence near those permanently shadowed craters and develops the technology to extract and process the ice will have a tremendous strategic advantage in the next era of space exploration. Now, let's shift gears, because there's a chapter of the moon's story that deserves its own long, careful telling. The chapter where human beings actually went there. Because the story of how we got to the moon is not just a technological achievement, it's one of the greatest engineering projects in human history, driven by Cold War politics and national pride and an almost reckless ambition that, against all reasonable odds, actually worked. And it starts with a speech by a young president who committed his country to something that virtually no engineer at the time believed was possible within the timeline he proposed. So let's set the stage. It's the spring of 1961. The Cold War is at full intensity. The Soviet Union has been beating the United States at every major milestone in space. Sputnik, the first artificial satellite, in October 1957, a profound shock to American confidence that triggered something close to a national crisis. Then Laika the dog in orbit. Then Luna 2, the first human-made object to reach the moon, in 1959. Then Luna 3, which photographed the far side of the moon for the first time. Grainy, blurry images, but the first glimpse any human had ever had of what's permanently turned away from us. And then, on April 12, 1961, the biggest blow of all, Yuri Gagarin became the first human being to orbit the Earth, completing a full orbit in 108 minutes aboard Vostok 1. The Soviets were winning, and it wasn't even close. The United States managed to put Alan Shepard into space 3 weeks later, on May 5, 1961, but it was a suborbital hop, 15 minutes and 28 seconds, up and down, not even one orbit. Impressive technically, but overshadowed by Gagarin. And the humiliation was compounded by the Bay of Pigs disaster in Cuba, a botched CIA-sponsored invasion that had happened just weeks before, making the Kennedy administration look incompetent. Kennedy needed a win, a big, visible, unambiguous demonstration of American capability. And his advisors, particularly Vice President Lyndon Johnson and NASA Administrator James Webb, told him the one area where America might leapfrog the Soviets was a manned lunar landing. In low Earth orbit, the Soviets had too much of a head start, but a moon landing was so far beyond either country's current capabilities that it was essentially a clean race. Commit the resources, and you could get there first. On May 25, 1961, Kennedy stood before a joint session of Congress and said, "I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth." Think about what he was asking for. At that point, The total American experience in human spaceflight was exactly 15 minutes and 28 seconds. Nobody had even orbited Earth in an American spacecraft. NASA didn't have the rocket, the spacecraft, the navigation techniques, the spacesuits, the landing vehicle, or the life support systems. They didn't even know for certain what the lunar surface was like. A Cornell astronomer named Thomas Gold had suggested it might be covered in deep, fine dust that would swallow a spacecraft like quicksand. The geologists argued against Gold, but nobody could be sure until you actually got there and stepped on it. Everything had to be invented from scratch, and they had 8.5 years. The cost would be staggering. The Apollo program ultimately cost about $25.4 billion in 1960s money, which is roughly 175 to 200 billion in today's dollars. At its peak, it employed about 400,000 people across 20,000 companies and universities. It was one of the largest peacetime mobilizations of scientific and engineering talent in human history. And it's worth noting that Kennedy himself wasn't particularly passionate about space exploration in a personal sense. He was passionate about competition, about winning, about demonstrating American capability in the Cold War. When he met privately with NASA Administrator James Webb, Kennedy was blunt about his priorities. The Moon program was, above all, a political statement, a demonstration of technological and organizational superiority that the whole world could see and that couldn't be disputed. The fact that it also produced extraordinary science was, from Kennedy's perspective, a secondary benefit. He wouldn't live to see the landing. He was assassinated in Dallas in November 1963, 5.5 years before Apollo 11. But the commitment he made that May afternoon in 1961, and the money and institutional momentum he put behind it, set the course that ended with human beings walking on another world. And the engineering challenges were almost beyond comprehension. Start with the rocket. The Saturn V, designed under the direction of Wernher von Braun and built by Boeing, North American Aviation, and Douglas Aircraft, remains the most powerful rocket ever successfully flown. It stood 363 feet tall, taller than the Statue of Liberty, and produced 7.5 million pounds of thrust at liftoff from 5 enormous F-1 engines. Each F-1 consumed about 3 tons of kerosene and liquid oxygen per second. 3 tons per second, per engine. The noise at launch was so intense it could be heard from 100 miles away. Each launch consumed roughly 960,000 gallons of kerosene and liquid oxygen in the first stage alone, which burned for just 2.5 minutes before being jettisoned. The whole first stage, 138 feet long, 33 feet in diameter, fell into the Atlantic, spent and abandoned. The engineering precision required was extraordinary. The turbopumps in the F-1 engines operated at pressures and temperatures that pushed the limits of metallurgy, and the combustion instability problem, random, violent pressure oscillations inside the combustion chamber that could tear the engine apart in milliseconds, took years and over 2,000 test firings to solve. Engineers would deliberately bomb the combustion chamber with small explosive charges to trigger instabilities, then modify the injector design until the engine could damp them out on its own. Trial by literal fire, repeated over and over until the engine was essentially unbreakable. Then there was the question of how to actually get to the moon and back. This seems straightforward, but it turned out to be one of the most consequential design decisions of the entire program. 3 approaches were debated. Direct ascent. One enormous rocket goes straight to the moon, lands, and comes back. This would have required a rocket even bigger than the Saturn V, a hypothetical beast called the Nova. Earth Orbit Rendezvous. launch multiple rockets, assemble the spacecraft in Earth orbit, then head for the Moon. This was the approach Wernher von Braun initially preferred. And Lunar Orbit Rendezvous. Send a combined spacecraft to lunar orbit, detach a small, lightweight lander, descend to the surface, rendezvous back in orbit for the trip home. This approach was championed by an engineer named John Houbolt, and initially, almost everyone at NASA thought he was crazy. Rendezvous in orbit around the Moon, 250,000 miles from home? If anything went wrong, no rescue was possible. But Houbolt was persistent, doggedly, almost obnoxiously persistent, bypassing the normal chain of command to argue his case directly to NASA's associate administrator. And the mathematics was on his side. Lunar orbit rendezvous required the least total mass to be launched from Earth, because the lander could be small and lightweight. It only had to operate in the Moon's 1/6 gravity, and it didn't need a heat shield for re-entry. All the heavy equipment for getting home, heat shield, parachutes, service module engine, stayed in orbit. It was elegant and efficient. In 1962, NASA officially adopted it. Houbolt's stubbornness had won out, and it's not an exaggeration to say that decision made Apollo possible within Kennedy's deadline. Any other approach would have taken longer and cost more. The lunar module, the LM, pronounced LEM, was built by Grumman Aircraft in Bethpage, Long Island, and it was unlike any spacecraft before or since. Designed purely for vacuum and the Moon's weak gravity, it had no aerodynamic shape. It looked like an angular insect wrapped in gold and silver mylar and Kapton foil. The crew cabin walls were astonishingly thin, in some places about 12/1000ths of an inch, roughly the thickness of 3 sheets of aluminum foil. A careless engineer once dropped a screwdriver, and it punched right through. Every ounce was ruthlessly eliminated. No seats. The astronauts stood, which was fine in 1/6 gravity. Small, triangular windows. No landing gear retraction. The legs deployed and stayed deployed. The descent engine was throttleable, essential for controlled landing. And the guidance computer, the Apollo guidance computer, designed at MIT's Instrumentation Laboratory under Charles Stark Draper, with software led by Margaret Hamilton, had about 74 kilobytes of memory and ran at less than 1 megahertz. Your phone is literally millions of times more powerful. But Hamilton's software was brilliantly designed, with a priority-based executive that could shed low-priority tasks under overload while keeping the essential guidance running. That feature would prove critical during the single most nerve-wracking minutes in the history of exploration. July 20th, 1969, Apollo 11, the lunar module Eagle, carrying Neil Armstrong and Buzz Aldrin, is descending toward the Sea of Tranquility. Michael Collins orbits alone in the command module Columbia overhead. During the powered descent, the computer starts flashing alarm codes, 1202 and 1201 alarms. Executive overflow, meaning it's being overloaded. The problem was a rendezvous radar switch left in the wrong position, feeding unnecessary data and consuming processing time. In Houston, a 26-year-old guidance officer named Steve Bales had seconds to decide: abort the landing or continue. He knew Hamilton's software was designed for exactly this. It would drop non-essential tasks and keep running the descent guidance. He called it, "We're go on that alarm." The landing continued. Then Armstrong looked out the window and saw the computer was guiding them toward a boulder field near West Crater, rocks the size of cars, too dangerous to land on. He took semi-manual control, pitching the LM forward, flying almost horizontally, skimming over the rocks, searching for clear ground. Mission Control called the remaining fuel. 60 seconds, then 30 seconds. At 30 seconds of fuel remaining, Armstrong was still flying, still looking. If he couldn't land in 30 seconds, he'd have to abort, fire the ascent engine, and abandon the attempt. He found a spot. He set the Eagle down. Contact light, engine stop. The margin between triumph and abort was about 25 seconds of fuel. Houston, Tranquility Base here. The Eagle has landed. Charlie Duke, the Capcom in Houston, replied with a voice cracking with relief. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. 6 hours later, at 10:56 p.m. Eastern Daylight Time, Neil Armstrong descended the ladder, stepped off the footpad, and placed his left boot on the surface of the moon. That's one small step for man, one giant leap for mankind. Whether he said a man or man has been debated ever since. Armstrong always insisted the A was lost in transmission static. Either way, the meaning was clear. A human being was standing on another world for the first time in history. The surface was fine-grained and powdery. The regolith, a layer of crushed rock created by billions of years of micrometeorite impacts, grinding the surface into a fine gray powder. It stuck to everything. It got into the seams of their spacesuits, coated their gloves, fouled equipment. Back inside the LM, when they repressurized and opened their helmets, the regolith smelled faintly of spent gunpowder, probably caused by the oxidation of reactive iron nanoparticles in the lunar soil when they first encountered moisture and oxygen. Those particles hadn't touched oxygen or water in 4 billion years, and the moment they did, they reacted. That gunpowder smell was chemistry happening in real time, ancient iron meeting modern air. They spent about 2.5 hours outside, much of it spent on tasks that had been rehearsed endlessly on Earth, but felt completely different in the moon's 1/6 gravity, where every step had an unfamiliar, bouncing quality, and the stiff, pressurized spacesuits made bending and reaching surprisingly difficult. They planted a flag, which has almost certainly been bleached white by decades of unfiltered ultraviolet radiation, since the moon has no ozone layer, no atmosphere at all to filter the sun's harsh rays. They deployed a retroreflector and a seismometer. They collected about 47 pounds of rocks and soil. Then they climbed back into the LM, sealed the hatch, rested, and fired the ascent engine. That engine, a single engine, no backup, no redundancy, had to work perfectly on the first try. There was absolutely no abort option. If it didn't fire, Armstrong and Aldrin would have died on the moon, and Collins would have come home alone. President Nixon had a speech prepared for that possibility, written by speechwriter William Safire. It began, "Fate has ordained that the men who went to the moon to explore in peace will stay on the moon to rest in peace." They never had to use it. The engine fired. It worked. Apollo 11 was followed by 5 more successful landings: Apollo 12, 14, 15, 16, and 17. Apollo 13, of course, never landed. On April 13, 1970, about 200,000 miles from Earth, an oxygen tank in the service module exploded, crippling the spacecraft. The crew, Jim Lovell, Jack Swigert, and Fred Hayes, lost most of their electrical power. Their oxygen supply was leaking into space, and they were hurtling toward the moon with no way to turn around quickly. They used the lunar module as a lifeboat, powering down the command module to preserve its batteries for re-entry, and executed a crucial engine burn using the LM's descent engine to swing around the moon and put themselves on a trajectory back to Earth. For 4 days, they endured freezing temperatures. The cabin dropped near 38 degrees Fahrenheit, limited water, and the constant question of whether the damaged heat shield on the command module would survive re-entry. It did. They splashed down safely on April 17th. It was a failure as a lunar mission, but a triumph of improvisation and human endurance, and it remains one of the greatest survival stories in the history of exploration. The later missions grew more ambitious. Apollo 15, 16, and 17 carried lunar rovers, lightweight electric vehicles that let astronauts explore miles from the landing site instead of staying within walking distance. Apollo 15 landed at the Hadley Rill, a sinuous channel carved by ancient lava flows at the foot of the Apennine Mountains. Apollo 16 explored the Descartes Highlands, seeking volcanic rocks and instead finding impact breccias, shattered, reassembled rock from ancient impacts, which taught scientists that the highlands were even more impact-dominated than anyone had thought. And Apollo 17, the final mission, in December 1972, went to the Taurus-Littrow Valley, a site chosen for its mix of highland and mare terrain. Harrison Schmitt, the lunar module pilot and the only professional geologist to walk on the moon, made a famous discovery at Shorty Crater: bright orange soil, which turned out to be tiny glass beads formed by ancient volcanic fire fountains, evidence of explosive eruptions on the lunar surface billions of years ago. Schmidt's excitement on the radio is one of the great moments in the history of geology. It's orange. It's all orange. I've never seen anything like it. The last humans to walk on the moon were Gene Cernan and Schmitt on December 14, 1972. As Cernan climbed the ladder for the last time, he looked out at the stark, beautiful landscape and said, "We leave as we came, and God willing, as we shall return, with peace and hope for all mankind." That was over 50 years ago. Nobody has gone back. For half a century, the most extraordinary footprints in human history have sat undisturbed in the lunar dust, slowly being eroded by micrometeorite bombardment, not by wind or rain, because there is no wind, no rain, and there hasn't been for 4.5 billion years. But the return is being planned. NASA's Artemis program aims to put astronauts back on the moon, focusing on the South Polar region and its water ice deposits. China's Chang'e program has been making extraordinary strides. Chang'e 4 landed on the far side of the moon in January 2019, the first spacecraft ever to do so, communicating through a relay satellite because the far side never faces Earth. Chang'e 5 returned samples to Earth in December 2020, the first lunar sample return since the Soviet Luna 24 in 1976. India's Chandrayaan 3 landed successfully near the South Pole in August 2023. The European Space Agency, Japan, South Korea, and private companies like SpaceX, Blue Origin, and Intuitive Machines are all involved in lunar plans. The moon is becoming a destination again, and this time, the goal isn't just to visit, it's to stay. Now, let's circle back to something we've been deferring: tides. Because tides deserve a deeper, more careful look. The physics of how tides work is one of those subjects that seems simple on the surface, but turns out to be genuinely subtle, and almost everyone's first intuition is incomplete. Here's what most people think. The moon pulls the ocean toward it, making a bulge on the near side. High tide, simple. And that's partly right. But it doesn't explain the most obvious feature of tides. There are 2 high tides per day, not one. If the moon were simply pulling water toward it, you'd expect one bulge on the near side and low tide on the far side. Instead, there are 2 bulges, one facing the moon and one on the opposite side, facing away. And that second bulge confuses people. Here's the key. Tides are caused not by the moon's gravitational pull itself, but by the difference in that pull across the diameter of the Earth. The moon pulls on everything: near-side ocean, solid Earth, far-side ocean, but it pulls harder on closer things. So the near-side ocean is pulled toward the moon more than the solid Earth beneath it is. The water bulges toward the moon, and the solid Earth is pulled toward the moon more than the far-side ocean is. The Earth, in effect, is pulled away from the far-side water. From the perspective of the far-side water, it's being left behind. So it bulges outward, away from the moon. Two bulges, opposite sides, separated by roughly 12 hours of Earth's rotation. That's your two daily tides. Now, here's something worth thinking about. The sun also raises tides. It's vastly more massive than the moon, about 27 million times, but it's also about 390 times farther away, and tidal force falls off with the cube of distance, not the square. That cubic dependence is why distance matters so enormously for tides, far more than for ordinary gravity. The moon's tidal effect on Earth ends up about 2.2 times the sun's. The moon dominates, but the sun contributes. When sun, Earth, and moon are roughly aligned, at new moon and full moon, the solar and lunar tidal bulges reinforce each other, producing especially high tides and especially low tides. These are spring tides. The word has nothing to do with the season. It's from an old Germanic word meaning to surge or leap forth. When the sun and moon are at right angles to each other, at first and third quarter, their effects partially cancel, giving moderate neap tides. This bi-weekly rhythm of stronger and weaker tides has been noticed by coastal peoples for as long as anyone can remember, and it's directly tied to the lunar phases. And it's worth noting that the interplay between tides and biology is profound. Tidal zones, the strips of coastline between high and low water, are among the most ecologically productive and competitive environments on Earth. Organisms in the intertidal zone have to survive being submerged and exposed twice a day, baked by sun and pounded by waves, and the evolutionary adaptations that have resulted are extraordinary. Tide pools, those small rocky basins that retain water at low tide, are entire miniature ecosystems. Sea anemones, hermit crabs, sea urchins, tiny fish, algae, all packed into a space the size of a bathtub, clinging to existence in a constantly changing environment dictated by the moon's gravitational pull. Isaac Newton, working out his theory of universal gravitation in the 1680s, was the first person to correctly explain why tides happen, and he was deeply satisfied that the same force pulling an apple toward the ground also pulled the oceans toward the moon. It was one of the great unifying insights in the history of science, and the moon was at the heart of it. In certain places, coastal geography amplifies tides to extraordinary extremes. The Bay of Fundy, between Nova Scotia and New Brunswick in Canada, has the highest tides in the world. The difference between high and low water can reach 53 feet. That's a 5-story building. You can walk on the ocean floor at low tide and be over your head in the same spot 6 hours later. The bay acts like a natural amplifier. Its funnel shape narrows and shallows, concentrating the tidal energy, and its natural resonant period happens to nearly match the tidal period, about 12.5 hours. It's like pushing a swing at its natural frequency. The amplitude builds and builds. The Bay of Fundy's tides are the most dramatic visible effect of the moon's gravity on Earth, and they've been doing this for millions of years, slowly reshaping the coastline, carving sea stacks and cliffs, creating one of the most dynamic landscapes in North America. And here's something that connects tides to deep time in a remarkably tangible way. Certain sedimentary rocks, particularly tidal rhythmites, found in ancient coastal and estuarine deposits, preserve daily and monthly tidal patterns as alternating layers of fine and coarse sediment. When the tide comes in, it deposits a layer of silt. When it goes out, conditions change, and a slightly different layer is deposited. Over months and years, these layers build up into a record of tidal activity that can be read like tree rings. By counting these layers in rocks from the late Precambrian, about 620 million years ago, geologists have determined that the day was only about 21 hours long, and the year contained roughly 400 days. The Earth was spinning faster, the moon was closer, the tides were stronger. It's all recorded in rocks that were once mud on ancient shorelines, compressed and preserved for more than 500 million years. Think about that. You can hold a piece of rock and read, in its layers, the length of a day, 620 million years ago. The moon's history is written in stone, literally. Now let's talk about eclipses. We've been circling around this topic all night, and they deserve their full moment, because eclipses are among the most spectacular phenomena you can witness on this planet, and the coincidence that makes them possible is one of those things that, once you understand it, fills you with a quiet, almost reverential sense of wonder. Here's the coincidence. The sun is about 400 times the diameter of the moon, about 864,000 miles across, versus about 2,160. But the sun is also about 400 times farther away from the Earth, about 93 million miles versus about 239,000. Those two ratios are almost exactly equal. And because of that near-perfect match, the sun and the moon appear to be almost exactly the same size in Earth's sky, each covering about half a degree of arc, roughly the width of your little finger held at arm's length. This is not caused by any physical mechanism. There's no law of physics that says a planet's moon should appear the same size as its star. It's pure coincidence. And it's temporary. The moon is receding, so it's getting slowly smaller in the sky. But right now, in this era of Earth's history, the match is close to perfect. And that makes total solar eclipses possible. During a total solar eclipse, the moon passes directly between Earth and the sun, and because it's just barely large enough, it covers the sun's photosphere, the brilliant visible surface, while leaving the corona exposed. The corona is the sun's outer atmosphere, a region of superheated plasma extending millions of miles into space, structured by the sun's magnetic field into delicate streamers and loops and filaments. It's always there, but normally it's invisible because the photosphere is about 1,000,000 times brighter. During totality, which lasts anywhere from a few seconds to about 7.5 minutes, depending on the geometry, the corona becomes visible, and it is astonishing. A pearlescent, ghostly crown of white light surrounding the black disk of the moon, with structure and texture that changes with the solar cycle. The inner corona glows almost silver white. The outer corona fades into gossamer streamers that reach out into the darkness like the petals of some impossibly delicate flower. The experience of totality is hard to convey in words. The sky darkens rapidly in the final seconds before the moon covers the last sliver of the sun. The temperature drops noticeably, sometimes by 10 or 15 degrees. Animals behave strangely. Birds roost, crickets chirp, horses become uneasy. The horizon takes on a 360-degree sunset glow, because far from the path of totality, the sun is still shining, and that light scatters into the shadow zone from all directions. Stars and bright planets become visible, and then there's the corona itself, shimmering and still, surrounding a hole in the sky where the sun used to be. People who see it for the first time frequently gasp, or weep, or stand in absolute silence. Veteran eclipse chasers, people who travel the world to stand in the path of totality, describe it as addictive, as a spiritual experience, as one of the most profound things a human being can witness. And it ends abruptly. A bead of sunlight breaks through a valley on the moon's limb. The brilliant diamond ring appears, and within seconds, the sun is back and the world returns to normal. The whole experience has a dreamlike quality, as if you briefly glimpsed something you weren't quite supposed to see. And here's what's poignant. It won't last forever. The moon is receding at 3.8 centimeters per year. About 600 million years from now, it will have moved far enough away that it can no longer completely cover the sun's disk. Total solar eclipses will cease to exist. They'll be replaced by annular eclipses, where the moon is visibly smaller than the sun, and a bright ring of sunlight remains around it, which are beautiful in their own way, but lack the corona, lack the totality, lack that primal, overwhelming darkness. We live in the window. We happen to exist during the narrow slice of geological time when the geometry works out perfectly. Our distant descendants won't be so lucky. Lunar eclipses are quite different, less dramatic, but beautiful in their own way, and the physics behind them is lovely. During a lunar eclipse, the Earth passes between the sun and the moon, and Earth's shadow falls across the lunar surface. But the moon doesn't go dark. It turns a deep, dusky red, a blood moon, though the term sounds more ominous than the reality warrants. Here's what happens. Earth's atmosphere acts as a lens, bending sunlight around the planet's edge and projecting it onto the moon. But the atmosphere also scatters and filters that light. The shorter wavelengths, blue and violet, are scattered away by Rayleigh scattering, the same process that makes our daytime sky blue. The longer wavelengths, red and orange, pass through the atmosphere and are bent toward the moon. So the only light reaching the moon during a total lunar eclipse is the filtered, reddened light of every sunrise and every sunset happening on Earth simultaneously, projected across 239,000 miles and painting the moon in their collective glow. That's what a blood moon is. It's the moon wearing Earth's sunsets. Throughout history, eclipses have terrified, inspired, and transformed. There are accounts of ancient battles being stopped mid-fight when a solar eclipse darkened the sky, the most famous being the Battle of the Hales in 585 BCE between the Lydians and the Medes, which according to Herodotus ended immediately when the sky went dark, both sides interpreting it as a divine command to stop fighting. Christopher Columbus, stranded in Jamaica in 1504 and desperately needing food from the local inhabitants, used his knowledge of an upcoming lunar eclipse to convince them he had power over the moon. When it turned red on schedule, they were so frightened they gave him everything he asked for. It's not Columbus's most admirable moment, but it demonstrates the psychological power of eclipses on those who don't understand them. The Babylonians, those meticulous record-keepers of ancient Mesopotamia, discovered that eclipses repeat in a cycle of about 18 years, 11 days, and 8 hours. This cycle, called the Saros, results from the alignment of 3 different periodicities of the moon's orbit: its synodic period, new moon to new moon, its draconic period, the time to return to the same orbital node, and its anomalistic period, the time to return to the same distance from Earth. When all 3 roughly coincide, the geometry repeats and a similar eclipse occurs. The Babylonians didn't know why the cycle existed. They had no model of the solar system, but they recognized the pattern and used it to predict eclipses. This was one of humanity's earliest predictive sciences, pattern recognition applied to the cosmos without any understanding of the underlying mechanism. And eclipses have served science in remarkable ways. In the 3rd century BCE, the Greek astronomer Aristarchus of Samos, a genuinely brilliant figure who proposed a heliocentric model about 1,800 years before Copernicus, used a lunar eclipse to estimate the relative sizes of the Earth and Moon. He noticed that Earth's shadow on the Moon was always circular, confirming the Earth was a sphere, and by comparing the shadow's curvature to the Moon's apparent size, he estimated the Moon's diameter at about 1/3 of Earth's. The actual ratio is about 0.27, remarkably close, using nothing but eyes and geometry from a Greek island 23 centuries ago. And in 1919, during a total solar eclipse visible from the island of Príncipe off the west coast of Africa and from Sobral in Brazil, the British astronomer Arthur Eddington photographed stars near the edge of the eclipsed sun and measured how much their apparent positions had shifted by the bending of starlight around the sun's mass, exactly as Einstein's general theory of relativity predicted. The confirmation was front-page news around the world and made Einstein a celebrity. The Moon, by covering the sun at precisely the right moment, had enabled one of the most important experiments in the history of physics. The Moon as scientific instrument, deployed by the cosmos itself. Now let's close this story, or at least bring it to a resting place, by talking about something less visible than tides or eclipses, something you can't observe with a telescope or feel at the shoreline, but something that may be more important than all the rest combined. The Moon's role in making Earth habitable. Because there's a strong argument, supported by rigorous computational modeling, that without the Moon, complex life on Earth might never have evolved at all. And the mechanism is subtle, elegant, and has to do with the stability of Earth's axial tilt. Here's the background, and it's worth laying out carefully because the implications are profound. The Earth's axis, the imaginary line running from the North Pole to the South Pole, the axis around which the planet spins, is tilted about 23.4 degrees relative to the plane of its orbit around the Sun. This tilt is what gives us seasons. When the northern hemisphere is angled toward the Sun, sunlight hits at a steeper angle and the days are longer. That's summer. 6 months later, the northern hemisphere tilts away. The sunlight arrives at a shallower angle, and the days are shorter. That's winter. It's not the distance from the sun that drives the seasons. Earth's orbit is nearly circular, and the distance varies by only about 3% over the year. It's the tilt, entirely, and this is true for every planet with a significant axial tilt. Now, Earth's tilt doesn't stay perfectly fixed. It oscillates, very slowly, between about 22.1 and 24.5 degrees, over a cycle of approximately 41,000 years. This is one of the Milankovitch cycles, named after the Serbian mathematician Milutin Milankovic, who worked out in the early 20th century how variations in Earth's orbit and axis affect long-term climate. The key point is that this oscillation range is small, 2.5 degrees of variation over 41,000 years. That's gentle. That keeps the seasonal cycle moderate and predictable. Summer and winter happen, but they don't become so extreme that the planet becomes uninhabitable. The tropics stay tropical. The poles stay cold. The temperate zones oscillate within a livable range. Complex life, with its forests and grasslands, its coral reefs and migratory patterns, its entire web of ecological interdependencies, can evolve and persist because the climate stays within tolerable bounds over the timescales evolution requires. But here's the remarkable thing: that stability isn't guaranteed. It's not a natural default. In the 1990s, A French astronomer named Jacques Lescar, at the Paris Observatory, ran a series of computer simulations that asked a seemingly simple question: what would happen to Earth's axial tilt if the moon didn't exist? The answer was alarming. Without the moon's stabilizing gravitational influence, Earth's obliquity, the technical term for axial tilt, would be chaotically unstable. Not just a little unstable, catastrophically unstable. Over timescales of tens of millions of years, the tilt could swing wildly, potentially ranging from nearly 0 degrees, meaning the axis would be perpendicular to the orbital plane, and there would be essentially no seasons at all, to more than 80 degrees, meaning the axis would be nearly lying flat in the orbital plane, and the poles would sometimes point almost directly at the sun. Think about what that would mean. At 80 degrees of tilt, you'd have periods where one pole receives constant, direct sunlight for months, while the other sits in total darkness. The temperature gradients would be savage. Ice sheets would build up to enormous thickness on one hemisphere and then melt catastrophically as the tilt changed. Weather patterns would be completely unlike anything the modern Earth has ever experienced. The gentle, rhythmic oscillation between ice ages and warm periods that has characterized the last few million years of Earth's history, that would be replaced by chaotic, violent climate swings that no complex ecosystem could track or survive. And here's the mechanism. It's not that the moon is holding the Earth's axis in place by brute force, like a hand steadying a spinning top. It's more subtle than that. The moon's gravity, acting on the slight equatorial bulge that the Earth has because of its rotation. The Earth is about 27 miles wider at the equator than from pole to pole, because the spin flings material outward, creates a torque that causes the Earth's axis to precess. Precession is the slow, circular wobble of the axis, like a spinning top that traces out a cone as it slows down. Earth's precession takes about 26,000 years to complete one full cycle. The axis traces out a cone in the sky, which is why the North Star changes over millennia. 12,000 years from now, the star Vega will be near the celestial pole instead of Polaris, and this precession, driven primarily by the moon, is what provides stability. Without it, or with a different precession rate, the Earth's axial tilt would be vulnerable to gravitational resonances with other planets, particularly Jupiter. Jupiter is enormous, about 318 times the mass of Earth, and its gravity exerts a subtle but persistent pull on Earth's orbit and orientation. At certain precession rates, Jupiter's influence can pump energy into the oscillation of Earth's tilt, driving it to larger and larger amplitudes, the same way pushing a swing at its natural frequency makes it go higher and higher. With the moon providing its particular precession rate, the Earth avoids these dangerous resonances. The moon tunes the Earth's precession to a safe frequency, one that doesn't resonate with Jupiter's influence, and the tilt stays in its narrow, safe range. Mars is a cautionary tale here, and it's worth pausing on. Mars has 2 tiny moons, Phobos and Deimos, named after the Greek gods of fear and dread, the companions of Ares in mythology. Phobos is about 14 miles across. Deimos is about 8 miles across. They're captured asteroids, most likely, irregular and potato-shaped, nothing like our spherical massive moon. And they're far too small to have any stabilizing effect on Mars's rotation. As a result, Mars's obliquity has probably varied chaotically over its history. Simulations suggest it may have ranged from about 10 degrees to over 60 degrees, swinging back and forth on timescales of millions of years. And some scientists believe this may be partly responsible for Mars's dramatic climate history. There's strong evidence that Mars was once warmer and wetter. Rivers carved channels across its surface. lake beds filled with sediments, minerals that only form in the presence of water, are scattered across the landscape. But that warm, wet period didn't last. Mars today is a frozen desert, with a thin atmosphere of mostly carbon dioxide, average temperatures of about -80 degrees Fahrenheit, and no liquid water on its surface. The loss of Mars's atmosphere is partly due to the lack of a magnetic field, but the chaotic obliquity swings may have contributed too, driving climate instabilities that helped strip the atmosphere over billions of years. The contrast with Earth is stark. Earth has a large, stabilizing moon. Mars has tiny, ineffectual companions. Earth has maintained a climate within livable bounds for billions of years. Mars swung from potentially habitable to frozen desert. Correlation isn't causation, and there are other factors involved. Mars's smaller size, weaker gravity, lack of a magnetic field, distance from the sun, but the obliquity stability that the moon provides is a significant piece of the puzzle. And this is one of those ideas that changes how you think about the moon. It's not just a pretty thing in the sky. It's not just a relic of an ancient catastrophe. It's not just a tide raiser or an eclipse maker. It's an active, ongoing, essential stabilizing force that has, for 4.5 billion years, kept Earth's climate within the bounds needed for complex life. Without it, you'd probably still have life. Bacteria are remarkably tough, and extremophiles cling to existence in acid hot springs and deep-sea hydrothermal vents, and inside Antarctic ice. But the gentle, temperate, stable world that allowed evolution to produce trees and fish and birds and mammals and, eventually, a species of primate that could develop language and agriculture and mathematics and telescopes and spacecraft. That world, your world, may owe its existence to a rock 250,000 miles away that you barely think about. That's an extraordinary debt when you stop and consider it. Your very existence, not just yours specifically, but the existence of complex life in general, may depend on a collision that happened 4.5 billion years ago between two objects that no longer exist, producing a companion that silently stabilizes the planet you're lying on right now, keeping it pointed in the right direction, keeping the seasons regular, keeping the climate within the narrow band that allows forests and oceans and everything that lives in them. And speaking of what comes next, the moon's story isn't over, not by a long way. We're actually at the beginning of a new chapter, one that may prove to be as transformative as the Apollo era, or perhaps more so, because this time, the goal isn't just to visit, it's to stay. NASA's Artemis program, named after Apollo's twin sister in Greek mythology, a fitting choice, is designed to return astronauts to the lunar surface, this time to the South Polar region, where those deposits of water ice in permanently shadowed craters represent a resource that could fundamentally change the economics of space exploration. The idea is to establish a sustainable human presence, not just a flags and footprints visit, but an ongoing program of habitation, resource extraction, and scientific research. A gateway station in lunar orbit, serving as a staging point, regular crewed landings. Eventually, perhaps, permanent or semi-permanent habitats built using lunar regolith as construction material, 3D printed structures possibly, using the fine-grained soil that covers everything. China's lunar program has been progressing with impressive steadiness. Chang'e 4 landed on the far side of the moon in January 2019, the first spacecraft ever to do so, because the far side is permanently turned away from Earth and direct radio communication is impossible, requiring a relay satellite placed at the L2 Lagrange point behind the moon. Chang'e 5 returned lunar samples to Earth in December 2020, the first sample return mission since the Soviet Union's Luna 24 in 1976, a gap of 44 years. And those samples, from a region called Oceanus Procellarum, contained basalts only about 2 billion years old, surprisingly young by lunar standards, pushing back the known end of lunar volcanism by perhaps 1 billion years and raising new questions about the thermal history of the moon's interior. China has announced plans for a robotic research station near the South Pole and has been developing crew-rated rockets and spacecraft that could support human lunar missions. India's Chandrayaan-3, which successfully landed near the South Pole in August 2023, made India the 4th country to soft land on the moon and deployed a small rover that detected sulfur and other elements in the polar regolith. Private companies, SpaceX with its Starship vehicle, Blue Origin with Blue Moon, Intuitive Machines with its Nova landers, are developing lunar transportation capabilities that could make access to the moon dramatically more frequent and affordable than in the Apollo era. The vision, for those who work in this field, is something that would have seemed like pure science fiction a generation ago, but is now within the bounds of engineering reality: a sustained human presence on the moon, using local resources, water for drinking, oxygen for breathing, hydrogen and oxygen for rocket propellant, to reduce dependence on supply from Earth. Lunar regolith contains aluminum, iron, titanium, and silicon, all of which could theoretically be extracted and used for construction and manufacturing. The moon's low gravity, 1/6 of Earth's, makes it an ideal staging point for missions deeper into the solar system. Launching from the moon requires far less energy than launching from Earth because you're climbing out of a much shallower gravitational well. There's also a purely scientific case for going back, one that goes beyond resource extraction and staging points. The moon is a time capsule. Because it has no atmosphere, no weather, no plate tectonics, and no liquid water, its surface preserves a record of solar system history that's been erased everywhere else. The ancient cratered highlands are essentially unchanged since the late heavy bombardment, 3.8 billion years ago. The regolith, that fine, powdery surface layer, contains implanted particles from the solar wind, recording the sun's activity over billions of years. Some scientists believe the moon may even preserve fragments of the early Earth, rocks blasted off our planet by ancient impacts and deposited on the lunar surface, where they've sat undisturbed in a way nothing on Earth could match. If you want to know what the Earth's crust was like 4 billion years ago, you might find the answer on the moon. The far side, in particular, is scientifically tantalizing because it always faces away from Earth. It's shielded from terrestrial radio interference, which makes it potentially the best site in the inner solar system for a radio telescope. A telescope on the lunar far side could observe radio frequencies that are impossible to detect from Earth, blocked by our ionosphere and drowned out by the cacophony of human-generated radio noise. It could listen for signals from the cosmic dark ages, the period before the first stars ignited, when the universe was filled with hydrogen that emitted radio waves at a specific frequency that has since been redshifted into bands our ground-based telescopes can't access. A radio telescope on the far side of the moon could, in principle, observe the earliest chapters of cosmic history. That's not a small thing. Will all of this happen? Some of it almost certainly will. Humans will walk on the moon again. That's a matter of when, not if. Permanent bases are more speculative, dependent on political will and funding continuity, which have always been the Achilles heel of every space program. Apollo was canceled not because it failed, but because the political will to fund it evaporated once the race had been won. But the technical foundations are being laid, one mission at a time, and the fact that multiple nations and private companies are pursuing lunar programs simultaneously makes this new era feel different from the last one. It's not a race between two superpowers anymore. It's a broader movement, with more participants and more staying power. The moon is once again a destination with a future, not just a place with a past. And you know, lying here thinking about all of this, the whole sweep of the story, from the cataclysmic violence of the giant impact to the quiet precision of tidal locking, from Anaxagoras's brave declaration that the moon was a rock, to Galileo's first astonished sketches, to Armstrong's boot in the regolith, from the ancient terror of eclipses to the delicate gravitational ballet that stabilizes our seasons, it's hard not to feel a kind of quiet awe at how deeply connected we are to this gray, silent companion. The moon doesn't do anything dramatic, not anymore. It doesn't shine on its own. It doesn't have storms or auroras or erupting volcanoes. It's geologically dead, airless, silent, covered in a fine gray powder that smells faintly of gunpowder and hasn't changed in billions of years. And yet, it controls the tides that sculpt our coastlines and drive marine ecosystems. It stabilizes the axial tilt that makes our climate livable. It slows the Earth's rotation, giving us longer, gentler days than we'd otherwise have. It inspired one of the greatest engineering achievements in human history. It provided the laboratory, the rock samples, the surface experiments, the retroreflectors that confirmed the age of the solar system, revealed the magma ocean, proved the giant impact hypothesis, and measured the distance to another world with millimeter precision. And it gives us eclipses, those rare, staggering moments when the geometry of three spheres aligns just so, and day turns to night, and the hidden corona blazes into view, and you're reminded, with a jolt, that the universe is beautiful in ways that go far deeper than anything you ordinarily see. The moon is moving away, slowly, centimeter by centimeter, year by year. In the deep future, billions of years from now, it will be much farther away, much smaller in the sky. Total solar eclipses will end. The tides will weaken to a whisper. Eventually, in the very distant future, tidal locking may work both ways. Earth's rotation may slow until the same side of the Earth always faces the moon, just as the same side of the moon always faces us. The day and the month would be the same length, something like 47 of our current days. The Earth and the moon would stare at each other, locked, synchronized, each face permanently turned toward the other, suspended in an eternal gravitational embrace. That won't happen for tens of billions of years, longer than the sun has left on the main sequence, so the question is academic, a thought experiment for cosmologists. But the physics is there, the process is underway, right now, tonight. But that's the deep, deep future, a timescale so vast it's almost meaningless in human terms. What matters tonight is this. For now, for this brief, extraordinary moment in cosmic time, the moon is close enough to touch with laser beams, close enough to visit in 3 days, close enough to see craters and mountain ranges through a pair of binoculars on a clear night, close enough to raise the tides twice a day, close enough to hold the Earth's axis steady while you sleep, close enough to be the first thing a child notices when they look up at the darkening sky and ask, with that mixture of curiosity and wonder that only children have, "What's that bright thing?" And there's something comforting in that, isn't there? Something almost like reassurance. In a life filled with uncertainty and change, the moon is the one thing you can absolutely count on. Tomorrow night it will be there, a little different in shape, a little more crescent, or a little more full, or a little past full and starting to wane. But there, doing what it's always done, reflecting light it didn't create, pulling on water it will never touch, holding steady an axis it will never feel. There's a kind of patience in that, a steadiness that has nothing to do with intention or awareness, and everything to do with the simple, reliable mechanics of gravity and light and time. The moon was there before you were born. It was there for your parents and their parents and their parents, back through every generation, every century, every millennium, all the way to the first human who looked up at the night sky and tried to make sense of what they saw. It watched the dinosaurs come and go, watched them for 165 million years, a span of time so vast that a Tyrannosaurus rex lived closer in time to you than to a Stegosaurus. It watched the ice ages creep down from the poles and retreat, creep down and retreat, over and over, grinding continents smooth. It watched the first fish crawl onto land. It watched the first mammals scurry in the shadows of reptiles. It watched the first primates stand upright and squint at the horizon. It watched the first campfires, the first farms, the first cities. It watched everything, from its quiet vantage point 250,000 miles away, turning slowly, always showing the same patient face. It's the most constant thing in the sky. The stars change, slowly, but they change, shifting, with the precession of the equinoxes, some dying, new ones igniting, planets wander, comets come and go. But the moon is there, every night, and in a world where everything seems to change faster than anyone can keep up with, where the news cycle churns and the seasons feel compressed and the years disappear like water through your fingers, there's something quietly reassuring about knowing that it will be there tomorrow night, and the night after that, and the night after that, doing what it's always done, reflecting a little borrowed light, pulling the oceans a little toward it, holding the world a little steadier. So if you're still awake, and really, it's fine if you're not, maybe let one last thought settle in, like a stone sinking slowly through clear water. The moon is out there right now. Whether you can see it from where you are or not, whether it's risen yet tonight or set already, it's there. A sphere of ancient rock, 2,160 miles across, turning once in 27 days, orbiting once in 27 days, reflecting 12% of the sunlight that touches its battered gray surface. It's raising tides in oceans you've never seen. It's holding the Earth's axis steady while you breathe. It's drifting imperceptibly farther away, 3.8 centimeters more than last year, 3.8 centimeters more than next year, on a journey that began with the most violent event in this planet's 4.5 billion year history, and won't end until the stars themselves grow cold. And the moon doesn't know any of this. It doesn't know it was born from fire. It doesn't know it stabilizes the climate of the planet next door. It doesn't know that creatures on that planet have walked on its surface and collected its rocks and measured its distance with beams of light. It doesn't know that right now, tonight, someone is lying in the dark, thinking about it, feeling that strange, quiet wonder that comes from realizing how vast the story is, and how small and brief and incredibly lucky any single life is within it. The moon is a rock, a big, old, gray, cratered, beautiful rock. And knowing its story, how it was born from fire, how it shaped the world you live on, how it inspired people to build impossible rockets and write love poems and work out the mathematics of celestial mechanics and stand in the path of eclipses and weep. Knowing all of that doesn't make it less mysterious. It makes it more so. Because the more you learn about the moon, the more you realize how much we still don't fully understand, and how deeply this quiet, patient companion, is woven into the fabric of everything. The length of your day, the rhythm of the tides, the changing of the seasons, the stability of the climate, the very possibility of the life you are living right now, in this moment, on this night, on this small blue world that has been turning beneath the moon's gaze for 4.5 billion years. Sleep well tonight. The moon will be there when you wake up. It always has been. It always will be. And that's enough. That's more than enough.